Hi, everyone. So today we're going to be going through the definite integral and some of its properties. This lecture is going to be a bit more technical than the last one. So if you do have any questions, please ask them at the end of the lecture. Okay, so to begin, let's define the definite integral. So definition of the definite integral. Okay, so previously we defined the definite integral as the limit of the Riemann sum. Okay, but now we're going to be a bit more technical and precise with the definition. So if f is a function defined for x values that lie between a and b. In other words, it's defined on the interval from a to b. We divide the interval a comma b into n subintervals. Remember, those were the widths of our different rectangles that we mentioned before, of equal width. Okay. And then that's going to be given by delta x is b minus a over n. Okay, so we divide the interval into n subintervals of equal width. Delta x equals b minus a over n. We then let x naught be a. So that's our first x value. x1, x2, dot, 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 up to xn, which we define to be b. That's our upper bound to the interval. Be the endpoints of the subintervals. Okay, so what does that mean? Well, it means from x0 to x1, that is the first subinterval, x1 to x2, that is the second subinterval, x3 to x4, sorry, that is the third subinterval, and so on. Okay, so this x sub r just labels the endpoints of our subintervals. Okay, and we let x1 star, x2 star, dot, 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 up to xn star be any sample points. We spoke about this before. Remember, given the subinterval, how do we define the height of the rectangle there? Well, we need to provide some x value in that subinterval such that f of x will give us the height of the rectangle. That chosen x point we call a sample point. Okay, so we've got this collection, or let's say it's the set of these. Let those be any sample points. You pick any in these subintervals. So x1 star is the sample point for the first subinterval, x2 star is the sample point for the second subinterval, and so on. And we see from 1 to n, that gives us our n subintervals, or the n rectangles that we spoke about before. Okay, so then the definite integral of f from A to B. So let's just highlight that. That's what we're defining. We're defining the definite integral of f from A to B is, and then remember we had that notation that we defined before, this elongated S shape from A to B, f of x dx. Okay, we came up with this notation is equal to, and remember from last time we said it was the limit of the Riemann sum. So we have the limit followed by the Riemann sum, where here we take xr star because we are taking any sample point. Okay, in that previous example that we did in the other lecture, we took the right endpoints. Okay, but remember it should work for any sample points. Delta x. Okay, so that's nothing new there. We had that before. Okay, but now there's a little bit extra that we need to add. Provided that this limit exists, okay, we don't want infinite values, so the limit needs to exist and gives the same value for all possible choices of sample points. So sorry, for all possible choices of the sample points. Okay, we don't want one choice to give a certain value and then another choice to give a different value. Okay, then this will be ill-defined because you can write this down, but then you might get one answer and your friend might get a different answer. Well, which one is correct? You can't tell. Okay, so we say that that is ill-defined. So we want that this gives us the same value for all possible choices. Okay, there's no ambiguity involved. Okay, so if it does exist, in other words, it satisfies these two conditions, we say that f is integrable. Okay, that's just a fancy way of saying that we can integrate f, or in other words, the definite integral exists. Okay, it all means the same thing. So we can integrate f, the definite integral exists, or f is integrable from a to b. It's all the same thing. So it's integrable on a, b. Okay, now just a little star here when I say integrable. Remember, we are doing this integration using the Riemann integral. So technically, we should be saying Riemann integrable. Yeah, because there is another notion of integration called Lebesgue integration, and then those have different conditions, and we say that functions satisfying those conditions are then Lebesgue integrable. Okay, so you've got Riemann integration, you do have others like Lebesgue integration. So technically speaking, we should put that in there. So this is the little star. Okay, but for now, we are only interested in Riemann integration. So whenever I say integration or integrable, or definite integral, anything like that, I am specifically referring to Riemann integration. Okay, so this is the definition of, let's put this all in here. This is the definition of the definite integral and the idea of Riemann integrability. Okay, so let's look at a little theorem on this idea of integrability, because as we will see, not all functions are integrable or Riemann integrable. So let's just make a little note here. Not all functions are Riemann integrable. Okay, so there's only a subset of functions that we can define a definite integral for. Okay, and we will see some examples of functions that can be integrated and some that can't be integrated. Okay, and then this condition of whether it can be integrated or not integrated, that depends on these two conditions here that we spoke about. Okay, so let's just highlight that here. So not all functions are Riemann integrable. Okay, so how do we know, sorry, how do we know if a certain function is Riemann integrable or not integrable? Okay, so we have a theorem for that. Okay, so theorem. If f, so our function f is continuous, okay, we know what that means. If it is continuous on AB, or f has only it has only a finite number of jump discontinuities. Okay, so f has a finite number of jump discontinuities. Then f is Riemann integrable so f is Riemann integrable on AB. And so the definite integral exists. Okay, so this is a very nice theorem. It tells us, or at least some functions are Riemann integrable. So all of the continuous functions are Riemann integrable, and so the definite integral exists. So remember what that means. It means the definite integral exists, which means it doesn't matter which sample points we choose. So if we can show, or if we know that a function is continuous, then we can choose any sample points. Like I did in that previous example, I chose the right end sample points and I got a value. Now this theorem tells me that I could have chosen any sample points and I would have gotten the same value, which is great. So that's the first thing. That's number one. If it's continuous, it's Riemann integrable. That's awesome. Or there's a second thing. F has only a finite number of jump discontinuities. Okay, so what does that mean? Let's take a look at an example of a function with a jump discontinuity. So let's see. So an example. So let's say we've got a function here maybe it takes on a constant value up to this point, and then it takes a different value after that point. Maybe this point is x equals 1. So let's say it goes from having a value of 2 to having a value of 3. Now, before x equals 1, the function is continuous, no problem there. After x equals 1, function's continuous, no problem there. However, at this point here, we see that there is a jump discontinuity. So we've got this function f, and it is definitely not continuous on R. Okay, because at this point x equals 1, it is discontinuous, so it is not continuous on R. However, this function is still Riemann integrable. Well, the theorem says that it's Riemann integrable. Okay, we trust the theorem, but also if we take a look at this picture, we can definitely find the area underneath this function. We've got that area there, or let's say from 0, and then let's highlight this area in here. Okay, definitely has an area, we can calculate it, and so it is Riemann integrable. Now, this isn't a proof or anything, this is just an illustration of the fact that we can actually find the area. So it is not continuous, but we can find the area. Okay, so in this particular example, we can find the area. Okay, and we see that this has a finite number of jump discontinuities. In this case, there's just one. Okay, let's look at an example with some more jump discontinuities, but still finitely many. That's the important part. So let's say it goes like this, then like this, then maybe like this, something like that. Let's call this f. Well, it is definitely not continuous. In two places here, it's not continuous. Over here, definitely not continuous, but we can still find the area. So we can find the area here. We can find the area here. And we can find the area here. So again, we can still find the area. Okay, so these examples, we call them step functions because it's like a little plateau or a step going over. But it doesn't have to be that. We can have other functions as well. Maybe something that looks like this. Something like that. It's a bit more complicated, but again, at this point here, we've got a discontinuity. Here we've got a discontinuity, a jump discontinuity, but we can still find the area. Over here, we can find this area. We can find this area here, and we can find this area here. Okay, so there's no issue with that. So if there's a finite number of jump discontinuities, then there is no problem. We can still find the area. And so the function is Riemann integrable. Now let's put a big but here. What happens if we have a function like this? F of x is equal to, and then it's split up into two parts, much like these functions here are split up into different parts. Let's say that it is 1 if x is rational, so all your fractions. So if x is rational, it's 1, and it is 0 if x is irrational. Okay, now this function, I don't even know how to plot this, but it is definitely not continuous. Because if you imagine one point that is rational, then right next to it could be something irrational. For example, let's say we've got here x and y. Maybe this point here is root 2, something like that. Then root 2 is irrational, so the function value is 0. But maybe, right next to it could be the rational approximation to root 2. You can think of it as root 2 to 1,000,000 decimal places. So that makes it rational. So then the function value is 1. But then right next to that could be something irrational again. So it goes down to here and then up there, down here. You see, it constantly alternates. So we have this constant alternating function. So it's never like a constant function for a little bit, and then 0 for a little bit, and then 1 for a little bit. Each individual point is either 0 or 1. So there's no area to this. Because you end up with just single vertical lines when the function is rational, and then 0 when it's irrational. You can't find an area for this. It doesn't work. Okay, so that doesn't work. So this function is not integrable. Okay, there's no way to find an area under this function. It doesn't make sense. Now, I should be more precise here and say Riemann integral. Riemann integrable. Maybe this function is integrable using another form of integration, maybe like Lebesgue integration, or something that your friend came up with. So it could be integrable in that case. But in this case, with this definition, it is not integrable. So we can't speak of a definite integral in this case. Okay, it just doesn't make sense. However, if we go back to our theorem here, where the theorem says that all continuous functions are Riemann integrable, that's very nice, because most of the functions that we work with and that I'm going to ask you to integrate will be continuous. Okay, or they might have a finite number of jump discontinuities. So in that case, you can integrate those. So we don't need to worry too much about whether the function is Riemann integrable or not. Okay, so if you can see it's continuous, that's more than enough to show that it is Riemann integrable. Okay, so that's just a little bit of technicality there. Now let's take a look at some properties of this definite integral. Okay, so properties of the definite integral. Okay, so just as a little note before we begin, always remember how the definite integral is defined. So the integral from a to b, f of x dx. Remember, that is just notation. We just wrote that down to make it look better. Remember that this is always the limit as n goes to infinity, the sum from I equals 1 to n, f of xr delta x. Okay, now from now on, I'm going to assume that f is integrable, which means we can choose any sample point. And so, I can choose the right sample point for everything, because it doesn't matter which one we choose. So from now on, we always assume that f is integrable. Okay, now that doesn't mean you ignore the conditions for integrability, but just for the sake of going through the properties, we assume that f is integrable. Okay, maybe for a tutorial question or a test question, maybe I'll give you something that is not integrable, and then you might have to explain why. Okay, but for now, let's assume that f is integrable, just so that we can look at the properties. So the key idea here is that the definite integral is defined in terms of a sum. Okay, so there's a bit more detail with regards to this, because it's not just a finite sum. Technically speaking, the sum is going off to infinity because n is going to infinity. So that makes things a bit more complicated than usual. But if we're careful with the limits and the limit laws, then we can use the sum properties to define integral properties. So the idea, with a bit of a complication on the side because it's an infinite sum, but the idea is use sum properties, like summation properties, to come up with integral properties. Now, not all of these properties of the sum is carried over because we do have this limits in front. Okay, so there's a bit of a complication with that, but some of the very useful summation properties, they do carry over to integrals. Okay, but not all of them, but we will get to that later. Okay, so some of the important properties. So, number one, the integral from a to b of f of x dx is equal to minus the integral from b to a f of x dx. Now, this is not because of any sum properties, but we see that on the left-hand side, the interval goes from a to b. So b minus a, that is a positive number. It's the width of the interval. So if we swap the endpoints of the interval and now go from b to a, then a minus b is going to be a negative number. So we got this minus sign. Okay, that's just because the width now becomes negative if we swap the endpoints. Okay, because remember, a less than b. Number two, the integral from a to a, f of x dx, is 0. Now, why is it 0? Well, the start of the interval is a, the end of the interval is a, so that means the width of the interval is 0. So there's no area there. If the width of the interval is 0, then there's no area. Okay, property number 3. The integral from a to b of some constant times f of x dx is equal to the constant times the integral from a to b f of x dx. In other words, we can take constants outside of the integral. So where did this come from? Well, remember that the integral is defined in terms of a sum. And sorry, if you have a constant inside the sum, remember that you can take the constant outside of the sum. And with limit laws, we can take constants outside of limits. So it's one hop out of the sum, another hop out of the limit, and so altogether we can take it outside of the integral. Okay, number 4. Just by the way, I'm not going to prove any of these now. Those are in your tutorial. Okay, to prove these, then you will have to attend the tutorial session, and then I'll go through those and then provide the solutions. Okay, so try it out for yourself first. Okay, number 4, the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b f of x dx, again plus or minus the integral from a to b g of x dx. Okay, so why does this make sense? Well, again, let's go back here. We know that the integral is defined in terms of sums. If I have the sum of AR plus BR, then I can always separate that into the sum of AR plus the sum of BR. I can separate the sums. Now, it's a bit more complicated because we've got the limit and infinite sum and so on, but that's the idea behind separating out the sums. Okay, that's what we did here. Also, that is exactly what we did in our example with the Riemann integral of x squared. Remember, we had the sum of a bunch of terms and we separated the sum onto each term. Yeah, we were using that property. Okay, number 5, the integral from a to b dx is equal to b minus a. Now, why does that make sense? Well, if we just think about this, another way of writing this is the integral from a to b of 1 dx. So if we think about this in terms of functions, the height of the function is 1. The width of the interval is b minus a. So what's the area? It's going to be 1 times b minus a, or just b minus a. Okay, which is what we have here. Okay, so that's all of the main properties that we need to know. So let's just zoom out here so we can see them all. Okay, so about 5 properties, and then you'll be using these properties to simplify your calculations. So we will use these to simplify calculations. Yeah, so if we have some integral with the sum of 2 functions, then we can split that problem up into 2 smaller problems. And then we do the integral for the first one, plus or minus the integral for the second one. Okay, so we can split our problems up like that. Okay, and then these other problems, these other properties are used quite a lot as well. Okay, the next thing that we will be looking at are some other properties of the integral, but they're not used for simplifying calculations, but we do need to go through them. Okay, so, oops. So, other properties. Okay, so like I said, these properties are not really used for calculation purposes, but they are good to know just because. Okay, so number 1. If f of x is greater than or equal to 0 on AB, then the integral from a to b f of x dx is also greater than or equal to 0. And we saw this last time when we were looking at the idea of positive area and negative area. If the function is positive, then that gives us a positive area. In other words, a positive definite integral. If the function is negative, then that gives us a negative definite integral. And if the function is both positive sometimes and negative some other times, then the definite integral means the net area. In other words, the positive area contribution minus the negative area contribution. Okay, and then number 2, if f of x is greater than or equal to g of x on AB, then the integral from a to b of f of x dx is going to be greater than or equal to the integral from a to b g of x dx. Now this makes some sense, because if one of the functions is always bigger than the other function, well, then you expect that the area under the first function will then be bigger than the area under the second function. Okay, provided the intervals are the same, because the heights of the rectangles for the first function are going to be bigger than the heights of the rectangles for the second function. Okay, and then property number 3. If little m, which is a constant, is less than or equal to f of x, which is less than or equal to capital M on AB, then m times b minus a is less than or equal to the integral from a to b f of x dx, which is less than or equal to capital M b minus a. Okay, so let's just do a quick proof of this last one here. So if we are saying that f is in the middle of little m and big M, what we are actually saying is that f is bounded. In other words, if we are going down, it doesn't pass some minimum value. So this is the minimum. And if we are going up, then it doesn't pass some maximum value. Okay, so we say that f is bounded. So if the function is bounded, then the integral is bounded. So we have some minimum value for the integral and some maximum value for the integral. Okay, so how do we go about proving this? So let's use property number 2 to prove this. So this inequality here, we can split into 2 parts. So we can say that m is less than or equal to f of x, and f of x is less than or equal to capital M. Okay, now we're going to use property number 2 to show that if f is greater than g, then the integral of f is greater than the integral of g. In this case, we have the integral from a to b m dx is going to be less than or equal to the integral from a to b of f of x dx. And the integral from a to b f of x dx is less than or equal to the integral from a to b m dx. Okay, and now we're going to use some other properties. Remember that this m can be taken out of the integral because it's a constant, this one as well. And then the integral from a to b dx is just the width of the interval. So this is m b minus a is less than or equal to the integral from a to b f of x dx, and the integral from a to b f of x dx is less than or equal to, again, same argument as before. This is going to be capital M b minus a. Now we can just combine these 2 inequalities into one, and we have that m b minus a is less than or equal to the integral from a to b, f of x dx, which is less than or equal to capital M b minus a. Okay, so we get our result here. Okay, and that's the last of these properties here. Okay, so that's it for today. If you do have any questions, please feel free to post them on that WhatsApp group, and or you can email me anytime, and I will get back to you as soon as possible. Okay, please keep a lookout for the next lecture that is coming up. Okay, it might be today or some other time in the week. Okay, see you next time.